All right, G4B test and monitoring equipment and two-tone test. What item of test equipment contains horizontal and vertical channel amplifiers? And the device that does that is an oscilloscope, which displays signal patterns on a screen. Traditionally, it was a cathode ray tube screen, but now more and more they're being displayed on computer screens. And they have a vertical input and a horizontal input. Now, very often the horizontal is generated internally, but you can also feed the horizontal, and you can do some things like frequency determinations like this. If you feed both the vertical and the horizontal with the same frequency in phase, you get a circle like this. Okay, if you feed the vertical and the horizontal with two frequencies, one of them being twice the frequency of the other, you will get a display like this and so on. So the oscilloscope can even be used by looking at waveforms to help measure frequency. So it contains both horizontal and vertical channels. The device is an oscilloscope. Which of the following is an advantage of an oscilloscope versus a digital voltmeter? The advantage is that complex waveforms can be measured. On the voltmeter, all we're going to see is some kind of a voltage that the voltmeter thinks should be an RMS voltage for a sine wave. If it's a complex waveform like this, the digital voltmeter readout will be pretty meaningless because it's going to interpret whatever it can get out of here as a sine wave and show you the RMS voltage. But if you want to actually measure the complex waveform, you need the oscilloscope. This is an example of a computer-based oscilloscope, and here you have all your controls here on the screen, and then the display is on the monitor right here. Which of the following is the best instrument to use when checking the keying waveform of a CW transmitter? Remember, a CW transmitter is turning the carrier on and off to make the signal. If you want to look at your waveform, you can use an oscilloscope to do that. Again, a handy device. In this case, we're looking at a series of dots being generated, possibly by our electronic keyer that we saw in the last section. And if you look at the waveform here, you can see that we have key clicks. The beginning of each of the dots has that spur up there, and that's a key click that's caused by the way the circuit's coming on. Okay, so what you would want to do to give yourself a nice clean CW signal is do whatever you needed to do to your transmitter so that that key click was not there, and that you had a smooth rise to this point and then straight across. But the oscilloscope lets you look at your keying waveforms of your CW transmitter. What signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal? You're going to take the actual output from the transmitter, you're going to attenuate it down to a strength that the oscilloscope can handle, and you'll be using the attenuated RF output of the transmitter on the vertical input of your oscilloscope. Why is high input impedance desirable for a voltmeter? One of the basic rules of any kind of measurement is that you can't measure something without affecting it. And that's especially true in electronics. And what happens if you use a voltmeter that has too low an impedance is you will load the circuit that you're trying to measure. And you can see that here. Here we have a simple circuit with a battery, an ammeter. We don't care about the ammeter right now. That could just be a straight wire across there. But we have a couple of other resistors in the circuit. And then we're trying to measure the voltage across this resistor here. Okay? Now, if the voltage, let's say that the voltage, the input impedance of this voltmeter was the same as this resistance, we'd get a totally erroneous value for this resistor because twice as much voltage, or correction, twice as much current would be flowing through the circuit because we'd have it flowing through here, and we'd have an equal amount flowing through here if the input impedance of the voltmeter was the same as the resistance. So you have to just decrease the loading on circuits as much as possible when you make measurements. Otherwise, you distort what's happening in the circuit, and you can't really get a good picture of what's happening there. What's an advantage of a digital voltmeter as compared to an analog voltmeter? The digital voltmeter has better precision for most uses, and you can see that here. Here we're measuring something with a digital voltmeter. It says 19.16 volts. Okay, here's an analog voltmeter, and you can see that reading 19.16, which would be right up in here somewhere, would be quite difficult with that. It would just be somewhere in there between the 19 and the 20 volts. Okay, here you see a more lab-grade voltmeter, analog voltmeter, and again you would need to read between the lines to get the kind of accuracy or precision that you see here with the digital voltmeter. Which of the following might be a use for a field strength meter? A field strength meter is a very simple receiver. In fact, it's untuned typically, a receiver that detects radio frequency fields and displays their strength on a meter. Okay? And normally has a sensitivity control. Normally is not tuned at all, so any radio frequency energy at any frequency will display on the meter. And it could be useful, of the options they give you here, it could be useful for close-in radio direction finding. So if you were quite close to a hidden transmitter or some other device that you're trying to determine its location, the field strength meter could help with that. Which of the following instruments may be used to monitor relative RF output when making antenna and transmitter adjustments? Again, the field strength meter is the instrument of choice here because it can monitor the actual RF output from the antenna or from the transmitter. So you can see on the meter where you're getting a stronger signal, where you're getting a weaker signal. You're actually detecting what's coming out of the system. Which of the following can be determined with a field strength meter? The radiation pattern of an antenna can be determined with a field strength meter. Now this is an illustration that I found in Google Images, and he has set up his field strength meter here on this step ladder, and he has his antenna set up here, and he's going to get relative strengths for his radiation pattern as his antenna, which looks like a horizontal Yagi. This is okay for an illustration, but in my estimation, everything's too close together there. And of course, that makes a better picture, but it probably would not work too well this way. Also, he's drawn a circle around here to move his ladder around, and the better way would probably be to put the ladder out somewhere more distant and turn the antenna to get the get the pattern. But anyway, here he's using a field strength meter to determine the radiation pattern of the antenna. Also, it would be a good idea, here we have horizontal polarization on our antenna, don't we? So it would be a good idea to make sure that your field strength meter had a horizontally polarized antenna. Which of the following can be determined with a directional watt meter? A directional watt meter. A directional watt meter shows forward power and reverse power. And this is one of the classic directional watt meters by a company called Bird Electronics. And what it does, it has a meter in here that is calibrated in watts. You have an input here. Typically, this one on the left is used from the transmitter. The one on the right goes out to the antenna. And then you have these slugs that go into this cavity in the meter body here, in the case of the meter. Okay, and here's a close-up of one of the slugs. This particular slug is calibrated for a full-scale indication at 100 watts. So you use the 100-watt scale over here on the meter, and then it's calibrated for a frequency range of 400 to 1,000 megahertz. Okay, and you put that in there, And with it in this position, with the arrow pointing this way, it will show forward power. Okay? If you turn it around so that the arrow is pointing the other way, it shows reverse power. And by knowing your forward power and your reverse power, you can go to either a chart or a formula to determine your standing wave ratio. It will not show you front-to-back ratio. It will not show you RF interference. It will not show you propagation. But it will, by showing you the forward and reverse power, let you calculate the standing wave ratio of your antenna system. Which of the following must be connected to an antenna analyzer when it's being used for SWR measurements? If you're making SWR measurements, you are typically making them of the antenna and the feed line, and that's what you hook up to your antenna analyzer. Antenna and feed line. This is a very popular antenna analyzer. I have one of these. It's probably, if not the piece of test equipment I use the most, it's probably the second most that I use. And here it's a really neat device. Here you can tune it to a frequency. Here it's been tuned to 7.1664 megahertz, and it's been connected to an antenna, and you can't really see much here except there's a thing there. But it's showing an SWR now for that whatever system it's connected to up to 2.1 to 1. Okay, so it directly reads SWR. It has a lot of other functions also, but a very, very useful device. And you can test your antenna without hooking it to a transmitter because you have a signal source inside the analyzer here that provides the signal to test the antenna. Very, very handy piece of test equipment. What problem can occur when making measurements on an antenna system with an antenna analyzer? If you have strong signals from nearby transmitters, that can affect the accuracy of the measurements. In fact, we have some repeaters that are co-located with FM transmitters on the same site, on the same hilltop. And in that kind of a radio frequency field, you can't use the antenna analyzer because the strength of the FM transmitter is just too much. You can't, the analyzer gets confused. So in that case, you have to use the directional watt meter or something like that to measure the SWR. So strong signals from nearby transmitters can affect the accuracy of the measurements. But for home use, for ordinary measurement of antennas and that sort of thing, that antenna analyzer is just a neat thing. What is a use for an antenna analyzer other than measuring the SWR of an antenna system? You can determine the impedance of an unknown or unmarked coaxial cable. You can actually estimate the length of a piece of coaxial cable without taking it off the roll. There are all kinds of neat things you can do in the book that comes with the analyzer, and it shows you how to perform those various functions. But determining the impedance of an unknown coaxial cable is one of the things that you can do with your antenna analyzer. What's an instance in which the use of an instrument? What is an instance in which the use of an instrument with an analog readout may be preferred over an instrument with a numerical digital readout? When adjusting tuned circuits, and if you think for a little bit, we talked about adjusting that vacuum tube radio frequency amplifier, didn't we? And if you think about that, adjusting that to the dip, and then adjusting it back up to the power that you want for your output, you can see that that's much easier with an analog pointer type needle than it would be with a digital device. So that's an instance where the analog type readout may be preferred because it lets you see more rapidly what's happening and also gives you a smoother indication of what's going on. What type of transmitter performance does a two-tone test analyze? It analyzes the linearity of your transmitter system. And again, here are those two-tone pictures again. And you can see that we have the good linearity here and the lack of linearity here. What signals are used to conduct a two-tone test? To conduct a two-tone test, you need to feed your single sideband transmitter with two non-harmonically related audio signals. Now, what does that mean? What does non-harmonically mean? If you have a 200 hertz signal and a 400 hertz signal, those are harmonically related because 400 is the second harmonic of 200. Okay, but if we feed it a 200 hertz signal and a 500 hertz signal, those are not harmonically related, and you could use those. All right, so two non-harmonically related audio signals are used to conduct the two-tone test.